All right, so we are going to continue our discussion of the visualization of forms and of n forms and or p forms and n vectors, I guess we'll call it. I keep having trouble describing things that are in the exterior power space. Those are p forms, and these things would be n vectors, where I've chosen 3 as my exemplar here. But we're trying to visualize these guys, right? All of these guys. And I'm going to make this first chart, this rubric, this important rubric. So we know that we have the set. Well, let's not even do it that way. We know we have the pair of one-dimensional scalar vector spaces that are essentially the bin of real numbers interpreted as either a 0 form or a 0 vector. They're totally isomorphic and identical. And flowing from those two, we get all of our exterior, what I'm calling the exterior product spaces. And since we're dealing with 3 dimensions in our story today, or in our visualization exercise, we stop at 3 because there's no 4th dimension. That means our underlying vector space V is 3-dimensional. And then likewise, we have the exterior powers of the vector space, like this. And important thing is that these can all be densitized, so we can get the exterior power of the tensor space tensor product, the top form of the of this covector tree, and likewise this can be densitized, and this would be 2 densitized, and likewise. Now it's interesting, we can densitize this guy, right? And what's interesting about densitizing this guy is you end up with essentially a scalar, because this changes with a coordinate transformation, the determinant of the transformation matrix, remember, and this changes with the reciprocal. So this whole thing does not change at all with so the densitized a densitized top 3 vector is this densitized 3 vector is isomorphic to a scalar, right? So we never kind of talked about it, but there's nothing stopping us from doing it. And likewise, if you do it this way, you can capacitate. So these are densitized. Densitized. How about with a Z? Why not? And these are capacitized. And that would be where you get what we would call a volume element, right? And like this. If we must. And then, of course, we know about duality relationships, right? The duality relationship without a metric present, so we're not talking about Hodge duals here, but this duality relationship will take 3 to, we'll connect these guys, and it will connect these guys, and it will connect these guys. And in particular, this space here, this space of 2 forms, is dual to the densitized, it's dual and isomorphic to the densitized 1 vector. So 0, 2 forms are isomorphic to densitized 1, 0 vectors. Likewise, 1 forms are isomorphic to densitized 2 vectors, right here, right? I actually don't want to have all of this green. I'm going to take all these green things out because I want to use this slide for other things, so I'll just point. These guys are isomorphic to these guys are isomorphic to these guys, and likewise these guys here are isomorphic to these. And notice these two here, this and this, they change in exactly the same way which is they don't change at all with the change of the coordinate system. All right, now let's take a look at this. I'm going to erase the middle, and we're going to try to systematically work through all of the combinations of things that we could make here. First, let's remember the arrow, right? That's an arrow. This is another word for arrow. This is the stack. This here was the thumbtack. And this is what we call the honeycomb. And remember, this guy over here is what we call the sheath, right? The sheath was this dual thing to the honeycomb. And this is all the Meissner, Thorne, and Wheeler work. And this is the Weinreich work. And that's actually going to cause a lot of confusion. To really lock down the visualization in here is not so hard. But when you start going to this sheath, you've got to now realize that the sheath has to work with dual objects out here, and things get a little bit more confusing. But I do want to tie it all together. I want to tie these two books together because the notion of the sheath and the notion of the honeycomb really are dual, and everything should work no matter how you look at it. And if you can move smoothly from there into here, you kind of really understand what's going on. But we're going to start by just focusing on the things that we know and looking at all the different operations we can do. And this is surprisingly little pictures we're going to draw. We're not going to draw very many pictures at all, but we have to sort of understand what is possible out there. So we know that we can take vectors and we can take stacks, right? And we can form the dual space mapping of a vector, or of a stack with a vector, right? A mu, E mu. And we know that that is a scalar, which is an element of the zero exterior power, right? So we know that these two can be combined to form that thing. So if we're going to call this an arrow, and if we're going to call this a stack, we might want to create notations that say an arrow can operate on a stack and get a scalar, right? And it equals sort of, I guess, an element of the real numbers, or a scalar. I'll just write equals scalar. How about that? Equals scalar. And the important part about a scalar is that no matter what you do to the coordinate system, scalar doesn't change at all. And that's exactly the way we expect it. This changes in exactly the opposite way as this. Remember, this is a density type object, right? It's I'm missing it. This object changes like a density. This object changes like a volume, right? In the quotations, right? It actually changes like a line, but it changes with a length, and this changes against a length. So, well, actually, I think the right word is this changes. This is a density style object. This is a volume or capacity style object, I guess is maybe the way to say it. It's a capacity style object. Capacity. Although, you know, again, all of these words sort of reference three-dimensional volume, right? Whether it's the space of the volume or the occupancy of the volume. So you have to sort of think of this in terms of just one dimension. This guy moves opposite of that guy. Anyway, the result is going to be a scalar. And so that is indeed one of the things we can do. And that is also exactly how Weinreich does it. This part is actually really simple. Our work has a direct parallel to Weinreich's work. So there's that. Then we can think about all the other possible combinations. Can we do something with an arrow and another arrow? Say an arrow C, because I've already used B. Well, we do know that if I take an arrow, we do know if I take a vector, A mu, E mu, and I wedge product with another vector, C nu, E nu, I can get a 2 vector, I might call it Q mu nu E mu wedge E nu, right? So I can wedge product things together. So here I've used the dual state space mapping operation, and here I've used the wedge product operation. Turns out those are really the only two operations available to us. So we have to go back here and look at all of these things, and all of these things, well, all of these things here, and we have to see what can I do by dual space mapping and wedging them together. What are all the possibilities, right? So this operation here, this guy here, we know we're calling a thumbtack, Q thumbtack. So we might want to write A arrow wedge C arrow equals a thumbtack. But we don't tend to do that because the wedge product, we always kind of have wedges preserved on both sides. We've used wedge product when something actually, the wedge product is designed for these types of objects, not these types of objects. So what we do is we create a new symbol there. We create a new symbol. This is a thumbtack. I'm going to erase this, and the new symbol is the cross product. So the cross product is going to take two arrows and produce a thumbtack. Now, why not just call this a dot product? Instead, call it a cross product. Well, I'm trying to stick as close as I can to Weinreich. Weinreich likes to use cross products for things that he considers to be of like type, and dot products for things that are of unlike type. And in his pantheon, things that are like type are arrow type. So arrow type things are arrows and sheaths, right? Things that you can that actually look like arrows. There's the arrow type, and the sheath is a density object, right? It's not a length object like the arrow, but it's drawn with arrows, and it's arrow type. And you can kind of see there, I mean, there's the arrow part of the sheath, so that makes some sense. And unlike type would be things that sort of cross this midpoint, right? If you were to sort of divide this thing down the middle, unlike type would go this way. So in his world, unlike types are stacks. Well, that's actually not correct. Wait a minute. So these two are of like type, and then he wants to call these two of like type. So because it's a stack, kind of, I mean, looks like a bunch of planes, and thumbtacks also look like little planes, right? And the relationship between stacks and thumbtacks is very similar to that between arrow and sheaves, because you have the object and then you have the densitized version. In this case, you have planes, and it's the density between the planes that matters the most, right? Or the only thing that matters is the density, the linear density of the stack. But the thumbtack looks like one little piece of plane, right? So these guys are plane type in Weinreich's world, and these guys are arrow type. So when we go back here and do our work, we say, okay, I can take a stack and I can wedge it with another stack, and I can get a two form. Well, a two form in Weinreich's world is called a thumbtack. And these guys are two similar typed objects. So because in his world, a stack is similar to a stack, we're going to use, an arrow is similar to an arrow, we're going to use the cross product, arrow, cross product, arrow equals thumbtack. So the point is you got to keep track of what he calls unlike and like. And then what we do in our work has always been basically these forms. I mean, this is your typical form algebra, right? There's nothing special at all about it. To us, this is very unremarkable. But to him, you got to be like, okay, we're going to create cross products between objects that I call like type objects. And by the way, those like type objects are sheaves and arrows. We wouldn't have even considered sheaves in our world. We would have been like, what are you talking about sheaves? They're honeycombs, right? But he jumps into this dual space, and he does that for. I mean, that's not a crazy idea. I mean, it's easy to visualize lines like this, densities of lines. It just becomes tough to go into one-to-one correspondence between the things we've been working with and the things that he wants us to work with, because he wants us to. This is to him. This is what you can visualize, right? Remember, this whole mess is caused because of the demand to visualize it. So if you must visualize it, and you want to make the contact with what we've been doing, you've got to go into his collection of objects, which are this collection here. Now, the alternative is to stick with this collection of objects, right? And which is Meissner, Thorne, and Wheeler's world, right? Meissner, Thorne, and Wheeler, those are his objects. Although he doesn't technically ever call a two vector a thumbtack, it's still, he uses it in effectively the same way. He does visualize the honeycomb and the stack and the arrow, though, and these are area elements, right? So he does all that. The problem is he does that in 4 dimensions, so there's some extra complications there, and that's why we're not literally doing it the way he did it. But either way, you should be able to put all of this together one way or another. So, so we've got that. We've got this operation down now. So we have what Weinreich would call the cross product. So far we've invented A dot B stack, and we've invented A cross arrow cross arrow. A cross stack equals scalar, and arrow cross arrow equals thumbtack. All right. So now, what else would we do? Well, we would do stack cross stack, right? Now, the stack cross stack, well, what can we do with 2 stacks, right? Well, we can wedge them, right? So when we wedge them, what do we end up getting? We end up getting a honeycomb, right? So we would call this a honeycomb, right? And it would be B mu E mu wedge. I shouldn't put a B there. This should be, say, I'll call it a D. Wedge D nu E nu, and this whole thing would be S mu nu E mu wedge E nu, and that's an obvious 2 form, of course, which we visualize as a honeycomb. So this is something that we would do, right? And it's nice and simple because it's all right inside this zone, and we basically we're just renaming forms with symbols, right? That's all we're doing. Unfortunately, necessarily in Weinreich's world, there is no honeycomb, right? A stack cross a stack has got to equal a sheath. It's got to equal a sheath. And that adds in, to interpret that correctly, adds in a layer of complication that we probably need to go through. So how do we take our simple process, which is A mu E mu wedge B stack cross a stack, sorry. It's A mu E mu wedge B nu E nu equals S mu nu E mu wedge E nu. That simple process of the wedge product of 2 1 forms becomes a 2 form. In the visualized world of Weinreich becomes stack equals sheath, right? And the operation that he wants to do is he wants to call this a cross product operation because these are 2 like objects. So we're going to call it some kind of cross product operation. So the way this would work in our language is we actually have to convert A from its vector form into its dual form defined through defined through this duality, or the duality from, or the isomorphism that goes from here to here, right? So there is this isomorphism where every form is a densitized, right? Densitized 2-vector. Just as every 2 form is a densitized vector, every form is a densitized 2-vector. So this isomorphism here is what we're going to have to work with. And the way we'll do that is I will write A as its densitized form, so I'll call it A alpha beta E alpha wedge E beta, right? But it's densitized, so it's tensor product E1 wedge E2 wedge E3. Now notice this alpha, A alpha beta, that's totally different than A sub mu, right? Because it has 2 different subscripts, this might as well be a different letter, but I'm trying to keep the letter A to show you, yeah, this is the dual of this, and you know it's the dual because it's got the same letter. So this guy here is isomorphic to that guy there, right? This stack, or this one form, has this isomorph. And but what is this thing? Well, this thing is an object that wants to consume 2 vectors, right? And one, oh, I can even put this in sort of, well, let me put that in red. So you sort of think of this as a single object. It consumes 2 vectors and 2 vectors and one element of lambda 3, right? The exterior product of the vector spaces, right? The top form of the vector spaces, top exterior power of the vector spaces. So if I make this substitution, right? If I take this and put it here, now instead of this vector product, I can still use my instead of using the vector product algebra to get this 2 form, right? What I'll do is I will just insert this form right here, and I will use the dual space mapping, right? And I will end up with, well, I'll just do it. I'll put B mu E nu like that. And what will end up happening is it consumes that guy, and it leaves behind something that takes a vector and takes a capacity, right, to give a real number. And of course, what takes a vector and a capacity to give a real number? Well, a sheath does that. So ultimately, this guy, when it's all worked out, is going to end up looking like S. The nus will get rid of the alpha, so I guess it'll be S beta E beta tensor product E1 wedge E2 wedge E3, which is a sheath, right? So that's one way to look at it. The other way of looking at it is to just go right to here and say, hey, wait a minute, that is a 2 form. I know that that's isomorphic to some sheaf S alpha E alpha tensor product E1 wedge E2 wedge E3. So that's sort of the logic that's going on here to make the connection for this cross product between two stacks to get a sheaf. And the sheaf, by the way, is arrow-like, right? So so far, the cross product has converted things. So you take 2 stack-like objects, you're going to end up in his world with this arrow-like object. So what else? What else do we have? We have, so now we've created that. I'll write down um, let's try, since I've been using A before, B stack cross D stack equals S sheath. So we've got that. So what else can we do? Well, we should be able to do something with an arrow and a honeycomb. Right? An arrow, we know that a honeycomb is a two form, an arrow is a one form. Two forms consume one form, so we can certainly feed one form to a honeycomb. And that, of course, is just trivial demonstration of the very almost the definition of things. So if our two form is S alpha beta E alpha wedge E beta, well, we'd feed it a vector A gamma E gamma. We leave one slot blank, and this whole thing's going to end up being C beta E beta, a one form. So that's pretty easy. So we should be able to write something like A arrow S honeycomb equals C stack, right? This is the honeycomb, here's the arrow, here's the stack. Now, the problem is do we call this a dot product or a cross product? When I say the problem, I mean the problem, it's really not a problem in any meaningful way, except that Weinreich uses dot products or cross products, and he likes cross products for unlike things and dot products for similar things. So the problem is he doesn't actually use the honeycomb, right? He uses the sheath. So we really can't call it one or the other, actually. So this thing doesn't really fit in his pantheon of dot products and cross products at all. But it is what it is, right? It is an operation between a honeycomb and an arrow, and that operation is totally trivial, regardless of what you call it. But we do want to make full contact with his work, so we have to. We obviously have to express the same thing as an operation between an arrow and a sheath, right? An arrow and a sheath, and those are like objects. So in his pantheon, he wants something that looks like arrow cross product sheath, because a sheath is an arrow-like object and an arrow is an arrow-like object. But it's still got to equal a stack, right? So how do we take an arrow and a sheath and make a stack? Well, what we're going to do is, of course, the sheath, we have to break it down into S alpha E alpha tensor product E1, and then we have this density, right? This one-dimensional density thing. That's the sheaf. So this sheaf, and now we've got this arrow and operating on that sheaf. So this is our version of a sheaf. Right? Now remember, Weinreich's version of a sheaf is just this thing plus a picture in your head of a bunch of arrows of a certain areal density, and given a certain direction, infinitely long. When I say arrows, I want you to think they're really, the important part of a sheaf. It's arrow-like, but they're infinitely long lines, right? Infinitely long lines that have a direction, right? That's really what it is. So don't think of it as a because the arrow actually is something of finite length with a direction. The sheaf is infinite length, but a density with a direction. This guy has no density concept. This guy has no length concept, right? So that is just an important distinction to make. Because sometimes I draw sheaths as though they're a bunch of finite arrows, and they look kind of like vector fields, but that's not correct, right? That's not the way to think about them. So now what we should do is, well, this sheaf, right, is isomorphic to what we were calling S alpha beta E alpha wedge E beta, right? So what we've done is we've found this sort of dual relationship isomorphism for the sheaf. Well, let's do the same thing for the arrow. So what would that look like? If you go back here, you say, okay, well, the arrow, its dual isomorph is the capacitized two form. There's the two form, and that's capacitized. It's the capacitized two form. So I can take a capacitized two form, and I can operate on a densitized one vector. And the result is going to end up being a, we're going to see in a moment, the result is going to end up being a stack, or a one form. So I will write this down as a alpha beta, I shouldn't use alpha beta, sorry, a gamma delta E gamma wedge E delta. Delta is like the worst delta ever. My tip here is a little bit too thick for this. E delta, tensor product, and what I'm going to do is I'm going to put a I'm going to simplify this. Instead of writing E1 wedge E2 wedge E3, I'm going to write that as a little box with an up arrow, and then the capacitized form, E1 wedge, E2 wedge, E3, I'm going to write that with a little down arrow. Right? So this will be with a down arrow. And you know, I could replace this here with the up arrow. I'll leave it there for now. So it's this guy and this guy. So what can I do with those two together? Well, I can actually, I can feed this to this, right? It won't fill up all the slots. It'll fill up this guy. What is it doing? It's looking for two vectors. You can just figure this out right away. You look at the tensor product, right? So everything on both sides of the tensor product is something that is representing a domain and a range. So we've got this thing is looking for a it's looking for two things. One is it's looking for some sort of density, right? Because this consumes a density to give a real number, and on this side it's looking for a two vector, right? A two vector, or it's looking for two vectors or a two vector. Remember, because of this universal property, it could actually go for either way. But the way we'll think about it is it's looking for, say, two vectors and a capacity. And that's what E gamma wedge E delta tensor product capacity is looking for. So then over here, if we feed this thing to it, well, we're feeding it a capacity because this is S alpha E alpha tensor product a density with an up arrow. So we feed that in there, and we end up with E wedge E delta tensor product capacity, and we have blank S alpha E alpha with the capacity, and this is almost a real number. The problem is it's missing a vector. Well, so it's an object missing a vector that would, if it had a vector, give you a real number. So this thing has to end up being just a capacity, which we'll call C gamma E gamma, like that. And so that's how ultimately, I think, we get from our logic, we get from our pantheon, which involves these densitized structures, into Weinreichs. Instead of saying arrow and honeycomb, which is, by the way, the easy way of doing it, what we do is we go, honeycomb actually becomes a capacitized two-form, or a capacitized two-form, right? Yeah, a capacitized two-form, and arrow becomes a capacitized two-form, right? This is not isomorphic to this. This is isomorphic to this. So arrow becomes a capacitized two-form, and honeycomb becomes a densitized one vector. And then we compare those two, and that gives us this cross product that Weinreich likes. So he would write A arrow cross S sheaf, right, equals C stack. Phew. Now, we haven't done much visualization yet, but let's actually visualize how that stack would get produced using his method. And the problem with this part is it's hard to kind of draw. But we have to remember a couple things. First of all, let's look at a stack from above, right? All these arrows, say they're coming out of this whiteboard. The only thing that matters is the density of the arrows. Their position in space doesn't matter. They can be shifted, moved around, and you can also shift the distance between the rows and the columns as long as you keep the density. So this form is precisely the same as, say, this form, right? As long as the number of arrows that penetrate an area stays the same. I guess here I have 5, so if same arrow I got, so I did a bad job, but in principle, if I make this distance big enough, I can shrink this distance as much as I want, and I still have what amounts to the same sheaf, because all that matters is the density. The density. All right, so that's looking at the sheaf from above. So now we have to kind of look at it from the side to do this construction. So let me change, the sheaf will be blue, right? So if we look at it from the side, I'll make 3 lines of the sheaf. All right, now these are 3 lines in one plane. So this would be, say, this line, and this line. And then the 3 lines behind it, we'll sort of look at it at an angle. And maybe I can change the thickness to a thinner thickness. And that line, and that line, and that line. So that's sort of these 3 here, right? So there's our sheaf sort of sitting in space. Now we have an arrow. So the arrow, I'll make the arrow back to the previous thickness. So the arrow is so that's our arrow A, and this is our sheaf S. So we want to form this A cross S to get a stack. So how might we construct a sheaf and an arrow together to get a stack? Well, what you do is we take the arrow and we move it into the sheaf so that the base of the arrow is right on one of the lines of the sheaf. Likewise, we could move the sheaf onto the arrow, or remember, this is all in some abstract tangent spaces being combined together, right? This isn't in real space, right? This is in, the arrow's in its own tangent space. So we can merge that sheaf and that arrow together in this construction. And once we do that, we kind of realize, look, that the tip of this arrow is not on the next line of the sheaf, is it? There's a mismatch. But fortunately, with every sheaf, I can readjust it, just like I said, right? Just like I said a moment ago, we can readjust the sheaf and not change it, and we can adjust these distances as much as we want. So let's do that, right? Let's do that so that we now adjust the sheaf so that two of the sheaf lines are exactly in conformity with this arrow that we're working with. And the price we pay, if it's much of a price, is that since I've expanded in this example, I'm going to have to narrow a little bit. So maybe these sheaf lines now are a little bit tighter, like that. So this group moves a little bit closer, but these two move a little bit farther, and we still preserve the sheaf. But we've constructed a sheaf that goes from the base of the arrow to the tip of the arrow in precisely the same way as with the same density. But what's happened is this plane here, there's a set of planes here, right, that can collect these arrows together. And that plane has moved a little closer. So now when I finish this construction, I have a plane defined by these arrows, and then a plane defined by those arrows, and that plane has a separation, and that plane is C. And then what is the orientation of C? Well, the orientation of this guy is like that. The orientation of this guy is like that. The right-hand rule gives me a curlicue like this, and then the right-hand rule on the curlicue gives me an arrow for the plane to come, say, slightly out of the board. So that's how you would make the construction A cross S equals a stack. And the construction with the honeycomb is virtually the same thing. Okay, so there we've done another combination. What else can we do? Well, we should be able to take a stack and a thumbtack and do something with that, right? A stack and a thumbtack should be, it's the same principle, right? A thumbtack is a two-vector. A two-vector is looking for two one-forms, and if I feed one one-form to a two-vector, I should get, what should I get? I should get an arrow, right? I should get a one-vector. So I should be able to create that object. So let's do that one. The idea here now is, let's see, oops, I don't want green. It's a stack and a thumbtack, right? So now we don't have to worry too much about densities or anything, because we're not dealing with sheaves. It's that sheaf. It's that choice to use a sheaf which complicates things a little bit to make this all jive together. But we know that we would write this as B mu E mu, and then we would write this as T mu, not mu, T alpha beta E alpha wedge E beta. And we could, the theory is we're going to take that and feed it into that. So we treat this as something that's waiting for two vectors, and we put, it was waiting for two stacks, waiting for two covectors, B mu E mu, and obviously this thing is going to end up being something of the nature of, well, we know what it's going to be. It's going to be C beta E beta. It's going to be an arrow, right? So now in Weinreich's prescription, what have we got? We've got a stack-like object or a planar type object with a planar type object. So this is also going to be a cross product. It's going to be plane type with plane type. So he calls it the same type of an object. If we go back here in our world, they're actually different type objects. These are, remember, these are our forms, right? These are our forms, and these are our vectors, right? So we kind of see these guys as whoops, we kind of see these guys as different type of objects, right? A 2 vector and a 1 form. But because this is a stack which looks like planes, and this is like a little piece of area which looks like a plane, I guess he says we're going to call them as like type objects. So it's kind of it's a completely superfluous distinction. Well, completely irrelevant distinction. Although it is a bit confusing. So how would we visualize that? Well, visualizing that, we are going to take a stack, right? So here's our stack, like this. And let's give the stack an orientation, say, it's easier to draw the orientation here, like it's coming sort of out of the plane, right? So there's our stack, and our thumbtack, remember a thumbtack is just a little thing of an area with an orientation, right? So there's our thumbtack. So just like we were able to completely and without any hesitation and without any concern manipulate the spacing of the lines in any one direction, as long as we conform to the density by correspondingly adjusting the other dimension, we can do the same thing with a thumbtack. The thumbtack, remember, the only thing that matters there is the area. So I can change the shape of this all I want. I can make it a long, skinny rectangle like that if I want, or I can make it a perfect square if I want. It doesn't really matter, as long as the area is the same. So I'm going to take this thumbtack, which is sitting in space and oriented in a certain way, and I'm going to squeeze it right in between this plane, like that, right? And I'm going to shape it so that its edges are right on the edges of the plane. So the edges are on the plane, and it's a rectangle, right? It would have to be. So but the point is it only intersects the plane. There's only one way to do this, right? There would be only one way to deform an arbitrary area so that it sits in between two planes with an exactly correct area, and it's a rectangle, right? So you do that. But what do you end up with? You end up with a little segment that is an arrow, right? You end up with an arrow. And that arrow is this segment that is part of that intersection. And the orientation is the right-hand rule going from the either the stack to the thumbtack or the thumbtack to the stack, depending on how you've written this. So in the way we've written this, it's stack first, thumbtack second. So you would go right-hand rule like this, getting that curly Q, and therefore using the right-hand rule on that curly Q, you would put the vector, I guess, like that, right? Yeah, that's I'm doing it with my thumb. You can't see it, but I'm doing it with my thumb. If I wrote it the other way, if I wrote it thumbtack cross product, then I would go the other way, and I would end up going from this vector into that one, and then my orientation would put the arrow over there. But remember, this is an arrow, so it's got a very precise length, so I should maintain the length of that thing. So that's the geometric visualization of that kind of construction. So we should write that in our list of things here, I guess. We would write B stack cross T thumbtack equals a arrow. All right. So, what about the dot products? I guess I've only gotten one scalar product in here. We should look at the rest of the dot products. All right, so what can we do with a thumbtack and an arrow? Thumbtack and an arrow. I don't think that's on our list yet. Thumbtack and arrow. No, it's not. So with a thumbtack and an arrow, let's see, an arrow and a thumbtack. Now we know the arrow is A mu E mu. We know the thumbtack is T alpha beta E alpha wedge E beta. So we can't feed them to each other, right? But we can wedge them together, right? We can wedge them together without any trouble. So when we wedge them together, we are going to get something that looks like, let's say, Q mu alpha beta E mu wedge E alpha wedge E beta. Well, that, of course, is an element of the top form of the exterior power, third exterior power of the vectors, right? So this is just a scalar capacity, right? It's a scalar capacity. It's scalar because we call it scalar because it's one-dimensional. So it's one-dimensional, so it's because we're in three-dimensional space and we've got a triple wedge product. And it's a capacity because it's this volume element here, right? This volume element here. So it does actually change with the coordinate system. If I expand the coordinate system, then this coefficient is going to have to shrink in order to keep this object to be the same. A regular scalar doesn't care. You can expand and contract it all day and it won't change. But a scalar capacity will shrink as you expand the scale of the coordinate system. So this object should exist in our pantheon, and indeed in Weinreich's world, these two objects are unlike, right? Because this is, he's calling this an arrow object, and this is a little piece of plane-like stuff. So he calls that a plane object. So he wants them to be the same. So this would be a dot product in his world, and that dot product ultimately we should write as a scalar capacity, which I guess would be some real number tensor product, I guess with the down arrow, right, is the way we're doing it. That's a scalar, right, down arrow? Yes, scalar capacity. So that gets added into our list of things now. Let's see. We now have, it was an arrow dot product thumbtack, right? That was what we just did. An arrow dot product thumbtack equals a scalar capacity. I'll just write that down. Scalar capacity. Phew. So then, I mean, by the same logic, you can almost see this one coming. If we can do those two, we should be able to do those two, and this will be a one form wedged with a two form, which gives us a three form. I'm not even going to go write this down. So one form wedged with a two form is a three form, and that's a scalar density. Now, again, we're dealing with Meissner, Thorne, and Wheeler's honeycomb visualization, not the sheaf visualization. So again, these two visualizations, we're going to have to resolve that. Not that there's anything to resolve, right? We just have to make sure we're clear on why it's the same, right? But what ends up happening here is that we're just adding another plane to the honeycomb, right? The visualization is pretty straightforward. I guess the visualization of the vector dotted into the thumbtack is here you have your thumbtack, and say here you have your vector. You just put the vector on the thumbtack, and you kind of sweep the thumbtack through the vector's direction, right? And it sweeps out a volume, and that volume is a cell, right? And that cell is a capacity. It's very similar to a parallelepiped, right? So that's the notion of a scalar capacity, right? Scalar capacity. Now, likewise, the other way was the stack dot product into the honeycomb, right? That ends up being a scalar density, where this honeycomb structure suddenly starts getting, so these are planes going like this, and these are planes going like this. Well, now you add planes going in this direction, and you chop up space into these little cubes, right? And these little cubes fill up this, this whole structure is only dependent on the density of these cubes. These are better what we should call cells, right? I used the word cells in a previous lecture, and I was actually looking at this honeycomb, and I was like looking at it from edge on, these things look like cells, but when you realize from the side, they're actually tubes, right? So it's much better to call these cells. And the top form will always be a cellular structure like this in any dimension, but in our case we can visualize it because it's only 3 dimensions. So that's what the scalar density will look like. Now, with a sheath, it's actually arguably even easier, right? Because, and this is one of the cases where the sheath doesn't seem to, well, in this case the sheath doesn't seem to hurt us because visually, because we just draw the sheath lines, right? So we're looking for a stack operating on a sheath, right? And it's got to give us some concept of a density. Well, we can build the sheath, and then we can slice the sheath with these planes, right? And what we end up with is a bunch of dots. Everywhere one of the sheath lines intersects the plane, we get a dot. And the dots will end up filling up space, right? As long as we have enough arrows, these dots will end up filling up space. And there'll be a certain amount of points per unit volume, right? So you're going to end up with these points per unit volume. And how would that structure look using the sheath definition? Well, let's see. It would go like this. The sheath would be S. Sorry, I'd like to keep this black. The sheath would be S alpha E alpha tensor product, and it's a density, right? So it looks like that, and then we have this guy, which is a stack, right? So what is the dual to the stack? Well, you could argue you don't even need that. You could just feed. Remember, this thing is looking for a stack, and it's looking for a capacity, right? So, but if you just feed it a stack, you're left with something that's looking for a capacity. So I should erase this capacity here. We know that it's looking for a capacity, but we're going to feed it the stack. We're going to feed it B, mu, E, mu, like that. And what do we end up with? Well, we end up with a density, right? And that's actually what we're after. We're after a density. So you can see how this would work, but it's a density that's reflected by just these points, right? These points everywhere. And basically these things are so obviously dual at this point because if you went to this cell structure, I don't want to call it a honeycomb, but the density structure, the cell structure, and you put a dot inside the middle of every cube, you would get the same density here as you would. Or if you took all the dots and you kind of shifted them to one corner, the density would always be the same. And likewise, you can manipulate the size and shape of the shape of the cells as long as this volume stays the same. And likewise, you can manipulate the distance between these points in any given direction as long as the overall density is the same. Likewise here, you can manipulate these little cells as long as the volume of each individual cell is the same so that the total density of cells is the same. And that kind of manipulation is very similar to what we did back here when we squeezed the thumbtack in between two planes, and over here where we started shifting the lines around to fit the vectors. And that's the geometry. That's all the visualization stuff, right? So what do we have? So now we have, what did I do? I did the stack dot product, the sheath to give a scalar density, right? So this was a scalar density. All right. Now, the scalar itself, so we have three types of scalars. We have scalar capacities, scalar densities, and straight up scalars. There is a way of looking at the straight up scalar where it is a capacity times a density, so it always cancels out. All right, so that, I think, completes it. Let me just check my notes here. Oh, no, there's one more, sorry. Notice we did a, we did a thumbtack and an arrow, right? So we did a thumbtack and an arrow, but we need to do a honeycomb and a stack, right? What we did was, where did we do? We did a stack and a sheaf in dot product form, right? But we didn't do we did a stack. I'm sorry, we did a stack and a thumbtack, but we didn't do. I guess we didn't do a dot product of sheaf and we didn't do this one. We didn't do sheaf and thumbtack, right? We did vector and, so we did vector and stack, but we didn't do sheaf and thumbtack. And these guys are dual to each other, right? So you can feed a sheaf to a thumbtack or vice versa. And what does that look like? Well, again, we just start with our usual thing. So the honeycomb, let's do the honeycomb version first. S alpha beta E alpha wedge E beta. Well, that thing is looking for two forms, right? But because of the universal property for antisymmetric multilinear maps, we know that we can also consider it to be a function. It can be considered to be a function looking for a single 2-vector. So we can feed a 2-vector in there to get us a real number. And indeed, that's what we're going to do. We're going to feed it T mu nu E mu wedge E nu. And that will give us a real number. And it gives us actually gives us a scalar, right? It's literally this is the dual space of this. So we're expecting it to give us a real number. For these finite circumstances, the dual space of two vector spaces is the dual space of the wedge product of two vector spaces is the wedge product of the dual spaces, right? So we know that we're going to get a real number out of that. And that's really easy to visualize because what we're going to do is we're going to have this honeycomb, which I'll just draw as though it's tubes, right? Right? And then thumbtack is an area, and simply you're asking how many tubes slice through this area. And the tubes have a direction, and the thumbtack has a direction, and so, but but that'll be whether the answer is a positive or negative scalar, right? So it's going to be positive or negative scalar. So if the directions are the same, you get a positive scalar. If the directions are opposite, you get a negative scalar. So that's pretty easy. In terms of the sheath, it's still pretty darn easy, right? Because now you just have this density of lines and the thumbtack, and you're just counting how many lines penetrated. It's the same thing, right? Each one of the sheath lines would thread a tube. And in that circumstance, you're now writing S alpha E alpha tensor product. It's a tensor product density, right? And your thumbtack is, your thumbtack is still T mu nu E mu wedge E nu. So now when you look at this, you take the essentially the isomorphic dual of the thumbtack to get T gamma E gamma tensor product capacity, right? So now we're looking at a one form, what is this? This guy is a capacitized one form, right? This is a capacitized one form. And this, of course, we know is a densitized one vector. So we finally actually have exploited the last part of this thing. Where was it? It was a capacitized one form, right? It's this guy, right? So we treat the stack as this guy and the thumbtack as this guy, and these guys are going to, and then you, and then after you've done that, right? You've got, wait a minute, no, it's a densitized one vector to capacitize one form. Yeah, so I got to go way back here. Sorry, it's a densitized one vector and a capacitized one form, and these are duals of each other, right? These are exactly duals, so you can feed one to the other, and you'll end up with a real number. And it has to be a perfect scalar, so it has no capacities or densities can be left over. So you're basically feeding this to this, and those two cancel, or that consumes that to give a real number, and this consumes this to give a real number, and you got a real number. So that's how you view it with in the form of the sheaths. Okay, I think that's all for now. So as a review, we've gone back to this guy. So I think I've this last one I should probably put in here, I suppose, which is it was a thumbtack, and I called that a thumbtack dot product a sheath, right? Arrow type and arrow type, right? No, plain type, unlike. So it's a plain type and it's plain type and arrow type. So, and that equals a scalar. So there's two ways to make scalar. Arrows penetrating planes and sheaths penetrating areas. And of course, that's just a counting process. This is Meisner, Thorne, and Wheeler's bongs of a bell, and this is just the number of tubes that cut through a plane in his book, and they both give you scalars. These other forms, these other countings, give you scalar capacities or scalar densities. So these guys actually change when the coordinate system changes, but these don't. And that makes perfect sense because you can never, there's nothing, if you just change the coordinate system in a continuous way, there's nothing that's going to take a tube on the inside and move it to the outside, or outside and move it to the inside. These arrows are always going to stay inside this closed curve. All right, so that kind of covers the hardest part of this visualization. The next part of it goes into the calculus, right? Stokes' theorem and integration. And we will do a brief discussion of integration in one of, we're getting down to the last lectures. I'm running out of topics here, but I do want to be comprehensive. So we probably will next move to integration. And we'll probably play around with this visualization stuff in this integration. But this is the bulk of the pantheon. This is how you visualize these things. And we'll talk a little bit more about how to squeeze these things into space-time. Because remember, we've kind of lost track of the fact that we're in a space-time with coordinate system, and at each point we have our vector space, our dual vector space, and then all of the other relevant vector spaces. And all of this activity here is actually going on in those little vector spaces at each point. We got to now start thinking about how to understand this stuff laying in space-time, and that gets us into this notion of the gradient of a function on the space-time. So you have a function of the space-time, and you could find the gradient of that thing, and that gradient is going to end up being a stack at every point in space-time. And sometimes those stacks can be meshed together, sometimes they cannot. When they cannot be meshed together, the difference in the meshing ends up being a sheath, right? So that'll be kind of interesting to see. So we'll get to that. So we'll start doing the calculus of all of this in the next lecture.